Hi, greetings from Team 12, Aditya Bhattacharya, Damodara Gadidasu, Manoj Mahato, here to present Project Chest XRay Disease Diagnosis. Our presentation will start with introduction to the project, then discuss about the dataset used and exploratory data analysis on the dataset, deep learning models used, an architectural flow diagram, approaches and methodology used, evaluation matrices, results and conclusion, improvements and future works, and finally the references used. Chest X-rays nowadays plays an important role in the diagnosis of thoracic diseases. Doctors extensively use artificial intelligence and computer vision based technologies for faster and accurate diagnosis of diseases. In recent times, various research works using deep learning based approaches have been published. Our project aims to replicate important aspects of earlier research work done, and we will try to improve the results by incorporating a new framework. For our project, we used downsampled CheXpert dataset consisting of 224,315 chest X-ray images of 65,240 patients. Exploratory data analysis on dataset shows data belongs to more male patients than female patients, concentrated between the age group 45 to 90 years. EDA also shows class imbalance and significant number of uncertain levels among the classes, along with lots of missing and null values unevenly distributed in the dataset. Over to you, Aditya.
Thanks, Manoj. This is how our overall architectural and process flow diagram looks like. So we have done the analysis on the downsampled version of the CheXpert dataset. Now the key steps involves exploratory data analysis, where we try to understand more about the data. Then we had to do the data pre-processing, basically like preparing the data in such a format that it can be fed into the model, which also involves for some of the algorithm like doing the feature extraction part. And then in the training phase, we normally use some of these algorithms to come up with various predictive model on the training data set. And then on the like we normally use the validation data set to do the model performance evaluation. Coming to the predictive modeling part, these are some of the algorithms that we have tried. The first one, LightNet 7, is something that we came up with. It is a 7-layer deep neural network that worked really well for some of the models that or some of the analysis that we have done. Then we have tried with DenseNet 1-to-1, like training the DenseNet on an entire image data from scratch. Then DenseNet 1-to-1 using the pre-trained ImageNet weights. And apart from that, we came up with a hybrid model which uses convolutional neural network for the feature extraction part, and for the classification part it uses classical machine learning algorithms like random forest, ADA boost, and XGBoost. Now we have also included extended features for this hybrid model, and these extended features are the age group, gender, and even the type of the image along with the images that we have used. Now coming to the architectural diagrams of the algorithms used. So this is how our 7-layer deep neural network or LightNet 7 looks like. And this is how our DenseNet 1-to-1 looks like, which is like as compared to LightNet 7, this is far more complex and it has far more layers. Now in DenseNet 1-to-1 using the concept of transfer learning. So here we use the pre-trained weights from ImageNet to extract features, and using the features extracted we normally do the classification and fine tuning on our data. Now for the hybrid model also it looks same almost, but in the classification part we have used classical machine learning algorithms like ADA boost, XGBoost, random forest, and these are some of the ensemble method that we have used. For this project, we have taken the individual class-wise binary classification approach, where we came up with 14 different models for the 14 diseases or the pathologies. Now, while doing the analysis, we faced the problem of imbalanced class, where mostly because the distribution of the data was not uniform. And to handle the imbalanced class problem, we tried the technique of upsampling of the minority class using the SMART approach, and that helped us improve the performance significantly. And coming up to the steps as mentioned before, like in data pre-processing, we have mostly done data scaling and even data augmentation, which is nothing but creating or generating virtual images by making certain transformations like flipping, sharing, etc. And then for feature extraction, using the transfer learning concept on the pre-trained weights from DenseNet 1-to-1, it really helped us in improving the performance to some extent. But we have also tried the hybrid model where the deep neural network was used for the feature extraction, and classical machine learning and ensemble methods like random forest and ADA boost, XGBoost were used for the final classification. For the model performance evaluation, we have considered different matrices like accuracy, precision, recall, F1 score, and AUC ROC scores. Apart from that, we have explored Hamming loss and model training and prediction performance rate, which is nothing but the execution time for each iteration as key performance indicators. Now, after referencing most of the research papers, we have seen that we thought of putting accuracy and AUC ROC scores, which we obtained from the prediction results on the validation dataset from the different models that we have applied. We observed that LightNet 7 was the fastest as compared to the other 5 models tried and most accurate in most of the cases. Now, the ensemble methods, although they were slow, but these improved the training time accuracy. But on the validation dataset, the results were not good as compared to LightNet 7 and DenseNet 1-to-1. Now, our results were slightly better than the results what were mentioned in the paper of Wang, Wandel, and Yao, but slightly worse than what was mentioned in the paper of Rajpurkar that we reference. Now, for the next section, Narendra will be taking forward.
Thank you, Aditya. Through this project, we came up with a framework to classify 14 pathologies wherein a DenseNet 121 trained on ImageNet was used for feature extraction and either a deep learning network or ensemble method was used for classification. We compared the models based on various metrics, primarily AUC and accuracy. Hybrid models were slower and performed poorly on validation set. As it was seen in previous slide, LightNet 7 worked better than others and it was faster to train. We faced challenges in handling null values and uncertain classes. Based on results of initial experiments, we dropped such cases. To handle imbalanced classes, we adopted SMART approach and we used dropout and data augmentation to handle overfitting. Because of infrastructure challenges, we were not able to use entire dataset for training. As SMART tries to oversample from entire dataset, it is slow, so we would like to come up with batch-wise SMART in future. We plan to try regional CNN for specific localization. Also, we would like to try U0, U1 and U self-trained models mentioned in CheXpert paper to handle uncertain labels. We have referenced various sources while completing the project and would like to thank the authors of them, especially those of CheXpert Dataset and the Deep Learning with Python book. Thank you very much and feel free to contact us if you have any query. Have a good day.